Welcome to the Passion for Technology podcast. In today's episode, we bring you an article readout from TQ Magazine, exploring the compelling vision of the all-electric society. For full access to the magazine, more insights, in-depth articles, and key facts, check out the show notes. The game changer for sustainable heating. Heat pumps are considered a key technology for the energy transition in the heating sector. They harness environmental heat and convert it into usable heating energy with the help of electricity. Due to their high efficiency and flexibility, they play a crucial role in reducing CO2 emissions. Space heating and hot water generation account for about half of the global energy consumption in buildings. Nearly 2/3 of heating energy comes from fossil fuels. In 2022, heating and hot water generation directly and indirectly emitted around 4.2 gigatons of CO2, representing more than 80% of the building sector's CO2 emissions. The Paris climate goals require a very conscious use of available resources. For heat supply, this means using as much available energy as possible and supplementing it as needed, explains Dr. Dietrich Schmidt from the Fraunhofer Institute for Energy Economics and Energy System Technology, IEE. Heat pumps utilize existing environmental heat and, with the help of electricity, raise it to a higher temperature level. As the required electricity is expected to be generated CO2-free in the all-electric society, heat pumps are a crucial component in decarbonizing the heating system. In addition, heat pumps help balance the energy system and can support the electricity grid. Since heat can be stored more easily than electricity, these systems can be combined with a water storage unit to heat in advance when sufficient electricity is available on the grid and is particularly inexpensive. Heat pumps fit well into a climate-neutral energy system, as they can operate in response to electricity supply. Through central grid-friendly control, they can turn on when solar and wind energy provide sufficient power. This contributes to smoothing out peaks in demand and supply in the electricity grid. This flexibility is a key component for a future energy system, says Dr. Dietrich Schmidt. The primary goal in advancing heat pump technology is to increase efficiency. A key factor in this is drive technology. By improving the power electronics of the inverters, which control the compressor, and depending on the type, also the fan, the overall efficiency of a heat pump can be enhanced. The use of silicon carbide semiconductors in the drive inverters can reduce losses in the entire drive system by up to 15%. Additionally, various manufacturers offer integrated power modules that manage the energy flow to the inverters. These modules include power semiconductors, as well as many passive discrete components. A typical power module replaces between 45 and 100 discrete components. The advantage of this solution is a smaller footprint and significantly shorter development times. In addition to classic compressor heat pumps, alternatives are also being developed. Conventional heat pumps use the two-phase Rankine cycle. In contrast, the heat pumps from the Vienna-based startup ECOP utilize the Joule cycle, where the working fluid does not undergo a phase change and remains in a gaseous state. Compression is achieved through centrifugal force. The working gas of the heat pump circulates in a closed loop that rotates around an axis. This rotational heat pump achieves significantly higher efficiency than conventional heat pumps, with a temperature lift of up to 100 Kelvin and output temperatures of 200 degrees Celsius. However, the heat pumps from the Austrian startup are, so far, true giants, 8 meters long and weighing 16 tons. Due to their high output temperature, they are primarily used in industrial processes. Researchers from various Fraunhofer institutes are taking a different approach. They are developing an electrocaloric heat pump that operates without a compressor. In this process, an electrical voltage is applied to an electrocaloric material made of special ceramics or polymers, causing it to heat up. Once the voltage is removed, the material cools down again. Using power electronics, the electrocaloric capacitors are charged and discharged several times per second, with heat being pumped in each cycle. The researchers have developed an ultra-efficient circuit topology for voltage converters based on gallium nitride transistors, achieving an electrical efficiency of 99.74% in the electrical power path. Achieving a high coefficient of performance in electrocaloric heat pumps requires very high efficiency in materials, electronics, and heat transfer, says Dr. Kilian Bartholomé, project leader and researcher at the Fraunhofer Institute for Physical Measurement Techniques, IPM. If we can master all of this, electrocalorics has enormous potential. We hope you enjoyed this article readout from our latest TQ magazine. To access the full magazine for free, just check out the show notes. Thank you for listening and stay tuned for more insights in our next episode.